Okay, it's time to move on to Module 7, which is going to cover sampling and sampling distributions. First, a little review from much earlier in the course. Recall that what we really want to get to in statistics is the topic of statistical inference. How can we use information in a sample to estimate or test hypotheses about a larger population? Recall that the population refers to all data of interest to the researcher, but most of the time we only have a sample of data, which is simply a subset of the population. Parameters are numerical characteristics of the population, such as mu, the population mean, whereas statistics are characteristics of your sample, such as x bar, the sample mean. Now, one of the interesting things about statistics is that a well-taken sample can give us very good estimates of parameters of the population. So far in this course, we haven't had much to say about sampling itself. That's an entire subject all to its own in statistics. But how you take a sample can be very important. And as I already said, even a very small sample can sometimes give you very good ideas of a larger population. Let's take up a little bit about what is called sample design and types of sampling. First, if we ask the question, what is a good sample? Well, kind of the obvious answer is we want what is sometimes called a representative sample. That is, we want the sample to be very similar to the population. Think, for example, you're all familiar with pollsters at election time. People go out and they take samples of people in order to try to estimate what percentage of the vote different candidates are going to get. Ideally, they want to take a sample that is going to be representative of the actual voting population come election day. Getting back to sample design, one of the other things we want to do is try to avoid what are called non-sampling errors. Kind of an awkward term, non-sampling error. A non-sampling error is actually a human mistake or something that could be avoided. It could be something as simple as punching in the wrong number into a data set. And we'll give some other examples in a minute. Well, if there's non-sampling error, then there's also got to be something called sampling error. And that's going to be something that we cannot avoid. Sampling error refers to the fact that there's always going to be a difference between parameters of the population and statistics in your sample, and it's inevitable. You don't expect the results of a sample to be exactly the same as the population. In class, I often use an example of supposing I took a random sample of 5 students from the room to estimate the average height of everyone in the room. Do I expect the average of the 5 people to be exactly the same as the average of everyone? Not at all. Like I said, that would be a miraculous stroke of luck if it happened. And that's what we mean by sampling error. There will always be that difference. One of the things that we want to learn about in this chapter and upcoming chapters is, can we measure that sampling error? A great example of non-sampling error occurred in the 1936 presidential election. Now we can see if you can remember your history. Do you remember who was running for president in 1936? Well, you should be able to remember the Democrat, if you know your history pretty well. Of course, the Democrat was Franklin Delano Roosevelt, who had already been elected in 1932 and was running for re-election in 1936. You probably don't remember the name of the Republican, and very few people would, except historians probably. But his name was Alfred Landon, and he went by Alf Landon. There was a magazine called the Literary Digest that sent out millions of questionnaires, and they got about 2.3 million back. And based on their questionnaires, they predicted that Landon was going to win quite easily, that he would get about 57% of the vote to 43% for Roosevelt. Come election day, not only were they wrong, but they were wrong by a massive amount. Roosevelt won the election with 62% of the vote, an absolute landslide, and a couple years later, the Literary Digest went out of business. Okay, now that particular viewpoint given in that YouTube video focused on a bias in the selection process. If you listen carefully, the Literary Digest sent out questionnaires based on telephone numbers and car registrations. Of course, back in the 1930s, a lot of people didn't own cars and didn't have phones. And so it's possible that this was biased towards upper income groups, which generally would be the Republican Party over the Democratic Party. There's at least one other viewpoint here. I'm going to take a look at this website here. Back in the 1970s, I believe somebody went back to the original data and said, there's no way the literary digest should have been that far off, even if they oversampled Republicans. They argued not only was there the problem with how they came up with their list of people they polled, the second problem that they had there what is sometimes called response bias. When you get a questionnaire in the mail, many people just take that questionnaire over to the garbage can and throw it away. And so there's always a question of, did we really get a random selection back or returned to us? What can happen in this case is people who feel very strongly about the issue become more likely to respond. And some writers have argued that this was another problem with the Literary Digest survey, that they got a very large response bias. So both of those are possible explanations as to what went wrong with the Literary Digest poll. Okay, let's move on to types of sampling methods. In general, there's going to be probabilistic sampling and non-probabilistic sampling methods. Probabilistic sampling methods use some form of random selection. And we're going to quickly talk about 4 different types here: simple random sampling, stratified random sampling, cluster sampling, and systematic sampling. You've probably all heard the term simple random sample. Technically, what a simple random sample is, if you're sampling from a finite population, you want to make sure in some way that every sample of size little n from the population of capital N items has an equal chance of being selected. For example, if I was going to pick 5 people from the class to form a committee, a random sampling method would say that every different group of 5 people should have an equal probability of being my sample. One way to do this is to use tables of random digits or random numbers, or these days, of course, computers can generate random numbers to help in order to take a random sample. Again, if you go online, there's all sorts of websites that have random digits or random integers. For example, here, let's just say I'm going to generate 5 random numbers that should be between 1 and 100. And I just click Get the Numbers, and here I have 5 numbers: 36, 69, 53, 13, 49. Now what I could have done here is, let's say I had 100 students and I was going to choose 5 of them. I could assign a number to each student, 0, 1, 0, 2, on up to 100. And then I could use a table of random digits to decide, okay, which 5 people am I going to select? So now I'm going to select number 36 and number 69 and so forth. In that way, I avoid any bias that I might have in the selection process. I simply let a random number generator take over. What if you're sampling from an infinite population? Well, then a random sample simply requires that all elements in the sample come from the same population and are selected independently of one another. About the closest thing in the real world that we can think of as an infinite population is, say, an assembly line process that produces parts and it goes on continuously. We could treat this as basically an infinite population. We would not be able to assign random numbers to each element of the population because it's infinite now. Okay, there's several variations on random sampling, and we're just going to take a quick look at some of these. Again, in a more advanced course on sampling, you can come up with all sorts of formulas for how to do these. One variation on random sampling is called stratified random sampling. You first divide the population into important groups, which we're going to call strata. Ideally, you would like the elements within a strata to be very similar. That is, little variation within each strata, but each strata is quite a bit different from the other strata, so there's more variation between the strata. You then end up taking a simple random sample from each stratum. You can either do this proportionally or disproportionately, and I'll come back to that in a second when I give you an example. A lot of election surveys are stratified samples. That is, you sometimes before an election know what the important voting groups are going to be, and sometimes those groups can become your strata in your sample. If gender is an important issue in an election, then male and female might be two strata that you want to account for. If race is important, you might want to make sure that you have the white vote, the black vote, the Hispanic vote. Those could also be then different stratifications. As it says at the bottom there, the more homogeneous the strata are, can often get by with a smaller sample size, or you can often do with a smaller sample size. Here's sort of an illustration of stratified sampling. I've taken my population here, and let's say I've broken it into 4 important stratifications. As I said before, ideally, most of the elements in group 1 here would be similar to one another, but they're quite a bit different from group 2, and so forth. Proportional stratified sampling would say if group 1 is 15% of the entire population, then I want 15% of my sample to come from that group. If group 2 is 20% of the population, I want 20% of my sample to come from that group. Sometimes you would deliberately disproportionately sample a group, especially if it had more variation to it. Here's a good example of a stratification. Consider here the state of Illinois. Take a statewide election. We already know some things about voting patterns in a statewide election. We know, for example, that the inner city Chicago vote is very heavily Democratic, and the downstate farm vote is much more heavily Republican. Those might become 2 important stratifications here. If the downstate farm vote is only 10% of your voting population, you might only want 10% of your sample to come from that group, and so forth. Something that's going to sound similar to stratified sampling, but it's going to be a little different, is called cluster sampling. Again, we divide the population into groups, and this time we're going to call them clusters rather than strata. But now the idea is exactly the opposite as it was for stratified sampling. You want each cluster to be very similar to the other clusters. In fact, each cluster contains all the relevant information that you're interested in. That is, it's kind of like a mini population. So you have very little variation between the clusters, but more variation within a cluster. When this can be done, you take a simple random sample of the clusters, and you can sometimes get by with simply sampling a couple of clusters, rather than sampling all the clusters. Since each cluster is very similar to the others, you can often take a random sample from 1 or 2 clusters. A couple possible examples. I have seen some sociological studies, for example, that like to look at life in big cities. In this case, New York, Chicago, Philadelphia, Boston. For sociological purposes, maybe all of those cities are fairly similar in terms of sociological characteristics. So rather than taking a random sample in all large cities, you might just pick 1 or 2 or 3 cities and simply sample from them and get a pretty good idea of the entire population. Another type of cluster sampling that I've heard about is what's sometimes called block sampling. This is especially used in rural areas and small towns where people want to gather some opinions or ideas about people in the town. But in small town America, it's often the case that most of the ideas and attitudes might be very similar. So rather than taking a random sample throughout the entire town, they might divide the town into city blocks and simply randomly sample within a couple of city blocks, and you can often get a very good opinion or idea of what the entire population looks like. You still again end up using a random sample once you've divided it into these clusters. Finally, for probabilistic sampling, let's look at systematic sampling. Sometimes taking a simple random sample can be too time-consuming. It might help to have a system. And that's exactly what we do with a systematic sample. We randomly pick the first item in the sample, and after that we let some system take over. Consider the example I give you here. A firm produces 20,000 parts every week. They like to take a weekly sample of 100 parts to check for defectives. Taking 20,000 divided by 100, that equals 200. What we could do is we could randomly pick the first part to inspect, and then choose about every 200th part thereafter. Since we chose the first part randomly, this is considered to be similar to a simple random sample. Okay, so far we've just looked at probabilistic sampling, but there is also what is sometimes called non-probabilistic or non-probability sampling. Convenience sampling and judgment sampling are two types. With non-probability sampling, we can't assess the probability of getting a particular sample. That is, we do not use any random method to try to guarantee a random selection. Convenience sampling, you're probably all familiar with different types of convenience sampling. It's just, as the title suggests, a convenient way of gathering data. How many times have you walked into a shopping mall and somebody walks up to you with a survey in their hand and asks you if you'd like to take a survey? Did they use any random selection technique necessarily to guarantee that they're getting a random view of the population? The answer is no. They'll just talk to whoever will talk to them. It's an easy way to gather some data. The disadvantage is you just don't know if your sample is very representative of the population. Another form of convenience sampling that you might have seen is many times on nightly news shows. They will ask you that if you feel one way about an issue to call this phone number, and if you feel a different way to call a different phone number. And so they allow your calling to determine the results that they get. Again, a possible problem with surveys like that is they might be liable for, or they might be susceptible to response bias, like the 1936 Literary Digest example that we looked at a few minutes ago. Finally, the last type of sampling is what we'll call judgment sampling. It's similar to convenience sampling, except you rely on the judgment of someone who hopefully is knowledgeable in the subject area that you're looking at to choose the items in the sample. You hope that somebody who has sufficient knowledge on the subject can do a reasonable job of selecting the sample. Again, however, it's very difficult to say how representative that sample would be. Okay, that's the end of part one. That's all we're going to do with our brief look at sampling. As I said, in more advanced courses on survey design and sample design, you can come up with complex formulas for how to take a stratified sample or a cluster sample and so forth. In the next part, we will look at what are called sampling distributions.